Swayam Prabha. Digital India. Educated India.
So, welcome to the 17th lecture on cryogenic engineering under the NPTEL program. In the last lecture, I will just give a brief outline just to see what we did in the last lecture. In the earlier lecture, we have seen that Kapitsa and Hellant systems, which are nothing but modifications of Claude system. In the Claude system, what we had was 2 to 3 heat exchangers and 1 expander, while in Kapitsa and Hellant, we had only 2 heat exchangers and 1 expander, and it has a kind of modification from the Claude system. Then we went to Collins cycle or Collins system, which is nothing but an extension of Claude system to reach lower and lower temperature. For example, liquid helium temperatures of around 4.2 Kelvin, wherein now 2 to 6 expansion devices are used. Collins system basically use more than one expansion device. The expansion device produces cold, and in order to reach lower and lower temperature, and depending on the mass flow rates or the amount of cooling effect what one wants to have, will decide the number of expansion devices that one wants to use in a Collins cycle, which is nothing but a modified Claude system. For a given pressure condition, that means if P1 and P2 or the inlet pressure to the compressor and outlet pressure to the compressor are known, the yield Y and the work done per unit mass of gas which is liquefied, this depend on the fraction of the gas diverted through expander 1 and 2, which are nothing but x1 and x2 as we saw last time, and the temperature at the inlet to the temperature, that is T3 and T5. So, if you see a Collins cycle, the yield from the Collins cycle and the work that is done per unit mass of gas liquefied, it depends on what are the values of x1 and x2, that is what are the fractions of the gas which are diverted through expansion device 1 and 2, assuming that there are 2 expansion devices, and also at what temperatures this gas is diverted from expansion number 1 and expansion number device number 2. Now, this is basically going to decide what is the value of Y, that is the yield, and the work done per unit mass of gas liquefied for Collins system. Now, in today's lecture, I am again going to talk about the gas liquefaction, and this is going to be last lecture now regarding gas liquefaction and refrigeration. What I am going to discuss now in brief are different components in a gas liquefaction cycle and also in a refrigeration cycle. The different components are heat exchangers, the compressors and expanders. In addition to that, having seen all these devices, having understood all these systems, having understood all these cycles, I would like to show you now how a particular cycle works. How does one get liquid nitrogen or how does one get liquid helium? That means, how does one reach 77 Kelvin to liquefy nitrogen, and also how does one reach 4.2 Kelvin to get liquid helium. So, I got some videos to show it to you, because we can't take you to the plants, but I got some videos from these plants, and let us try to understand how this cycle happen. But in cryogenics, you can't see anything closer, because everything is enclosed, everything is under vacuum condition. So, one cannot really see what is happening inside, and therefore, what you see is only from outside. Everything is under vacuum, everything is at very low temperature and not accessible from room temperature. So, you will have to see what I will tell you as to what exactly there inside this vacuum device. Also, I will like to have a comparison of different systems so that one gets feel of different liquefaction cycles. There are different liquefaction systems where I will just show a small comparison, assuming that the pressure ratios are known to us. And finally, I will summarize what all we did during the last 10 or 12 lectures, in which we covered gas liquefaction and refrigeration system. In the earlier lectures, we have seen that various gas liquefaction and refrigeration system, and we have seen that the various components like compressors, expanders, heat exchangers are absolutely critical to the performance of the system. We had seen that how effectiveness of heat exchangers matter, how does it affect the yield, also different efficiencies related to compressor and expanders, how do they affect the yield and the work done per unit mass of gas which is liquefied. These processes of compression, expansion, heat exchange, that occur in these components are irreversible and deteriorate the performance of the system. Hence, why are we studying all these things? Because we know that these are very significant, they have very significant effect on the liquefaction, and therefore, there is a need to study about these components that are used in this system. So, we should know what kind of heat exchangers are used, what kind of expanders are used, what kind of compressors are used, what are the problems with these units. Although we cannot go into details of all these system components, at least what we can do is we can touch upon briefly to see how these components work. So, first we come to the heat exchangers, which is a very important component of the liquefier. The heat exchangers are the most critical components of any liquefaction system. They are used to conserve cold by heat exchange between the high pressure hot gas and the low pressure cold gas. We know that the low pressure gas, after liquefaction, the remaining gas goes back, and this is cold gas, and therefore, whatever cold it is carrying, we use this cold to pre-cool the incoming hot pressure gas, high pressure gas. Now, this graph tells you the variation in the value of Y, that is the yield, with the epsilon value. So, you can see that if the epsilon value or the effectiveness of heat exchanger is 100%, we got a very high yield, or the highest yield around, let us say 0.09 or something like that. But you can see as the epsilon value goes down from 100% to 95% to 90%, the yield starts coming down. So, this curve tells you how important it is. And what you can also see from this, if your epsilon value or the effectiveness value is less than 85%, the yield is absolutely 0. That means, it is essential that your yield or your heat exchanger effectiveness is somewhere close to 95%, so that you get a good value of Y, so that you get a reasonable value of Y. Definitely, when one can't reach 97%, 98%, because there are fabrication limitations, there are assembly limitations, there is pressure drop in the system. All these things have to be considered while design a heat exchanger, but at least one could strive to attain at least 95% effectiveness for heat exchangers. And therefore, we know that the effectiveness of heat exchanger has to be more than 85, and if one wants to have a good Y value or a reasonably good Y value, the effectiveness has to be, let us say, more than 90 or 95%. What are the requirements of heat exchangers? Now, in order to qualify to be a good cryogenic heat exchanger for gas liquefaction, it has to satisfy certain criteria, it has to satisfy certain requirements. And what are these requirements? The requirements are, it has to have high effectiveness with minimum pressure drop. It has to be a compact heat exchanger. Now, this is very important, because in cryogenic, if you got a very big heat exchanger, for example, if you got a shell and tube heat exchanger, lot of cryogen will be utilized to cool the heat exchanger itself. That means, it will have a lot of mass, and therefore, in cryogenics, the cool down time will be very high. When you start the liquefier, it will take a lot of time when the liquefaction starts. So, therefore, one has to have a very compact heat exchanger, and what does it mean? It should have a high heat transfer area per unit volume. If we say that if the heat transfer area per unit volume is more than 700, then it's normally called as compact heat exchanger. So, one should strive to go in a compact heat exchanger area zone as far as cryogenic heat exchangers are concerned. We should have therefore minimum mass with multi-channel capabilities. If you got multi-channel capabilities, you can have more flow rates, more heat transfer area also. One should have definitely high reliability with minimum maintenance, and these are very general criteria. What is most important is high effectiveness and the compact heat exchanger. Now, there are different configurations that are possible for heat exchangers to be used in the cryogenic heat exchangers, and they are tubes in tube, bundle tubes, fin tubes, and plate fin heat exchangers. So, different kind of heat exchangers could be used, and in order to maximize the heat transfer area per unit volume, we can have various structure. We can have many tubes in tube. We can see that in the next slide. We can have fin tubes. We can have plate fin heat exchangers also. And as you know from different cycles, what we have seen, heat exchanger can be of 2 fluid or 3 fluid types, depending on the heat exchanger and cycle we are talking about. So, normally the heat exchangers are called Linde tube heat exchangers, which are commonly used in liquefaction systems because they were invented by Linde and used by Linde. So, you can see here a tube in tube heat exchanger where the high pressure gas goes inside the tube and the low pressure gas comes over the tube. So, it is a tube in tube kind of heat exchanger or Linde concentric tube heat exchangers. Then instead of one tube, we can have 3 tubes in one tube. So, Linde multiple tubes heat exchangers. They are pretty simple to understand from here. So, here we can have a coiled structure of the heat exchangers, and the high pressure gas can go in the inner tubes, while the low pressure gas can come above this tube. Now, one can have a Linde concentric tube heat exchanger with a wire spacer. So, the low pressure gas which is coming over can see this turbulence which is created by this wire spacer, and therefore, the heat transfer area on the low pressure side could be increased in that case. We can have bundled heat exchangers like this. So many solder structure is available of so many tubes over here, and you can have heat transfer between different tubes. The tubes in tube type heat exchangers, as you can see over here, are the simplest of all types in terms of construction. So, all these heat exchangers are actually called tube in tube, and they are simple heat exchangers. For manufacturing point of view, they are simple, but the amount of heat transfer area that is available here could be limited. They may not be classified under what you call as a compact heat exchangers, but they are still used in cryogenic heat exchangers. These have low cost and are well suited for high pressure applications. All these heat exchangers for large flow rates, one goes for 3 tubes are used in a bigger tube or a 3-channel heat exchanger. So, we can have different flows through different tubes also. The use of a wire spacer or a turbulator like what you can see over here on low pressure side acts as an extended surface and enhances heat transfer on the low pressure side. I think this is mostly clear because many of these things possibly you have understood or you have covered in a heat transfer or heat exchanger courses. Now, very typical kind of heat exchanger which was used by Collins, and therefore, it is normally called as Collins heat exchangers. And what you can see here is a fin tube and shell kind of a heat exchanger. Basically, what you can see are different fin tubes wound around a mandrel. So, you can see a mandrel over here around which concentrically arranged fin tube are there, which you can see in top view here. They are all fin tubes. The high pressure gas goes to the inner tube over here, while the low pressure gas, the high pressure gas goes in a coiled form. It will come down the end, it will get expanded, and the low pressure gas will go over these fins, and then it will come out of the top. And you can have various layers of this fin tube, so that you get higher heat transfer area available in a given volume. So, the Collins type heat exchanger consists of several concentric copper tubes with an edge wound copper helix wrapped in annular surface. So, what I am calling as fins could be a edge wound copper helix which acts like a fin, alright. And therefore, what is most important is what is the contact of this copper helix with the main tubes over here. Therefore, the fin efficiencies or the contact resistance should be 0 and the fin efficiency should be higher in this case. This helix acts as a fin and enhances the heat transfer area. The heat transfer area on the low pressure side, the low pressure side gas sees these fins, while the high pressure gas goes inside the tube. And as you can see, we can have 2 layers, 3 layers depending on the kind of flow rates which we are talking about, and corresponding to that whatever heat transfer area required, one has to calculate and accordingly design this heat exchanger. In this heat exchanger, the high and low pressure streams flow in the inner and outer passages respectively. So, the high pressure gas goes through this inner tube, while the low pressure gas come over the fins in a coiled manner. The tubes are stacked like this and the gas will come over these fin tubes. You can see the same thing over here, where you can see that the coiling is done over here. The high pressure gas will come through this tube, while the low pressure gas will go over this tube. And this is basically kind of a shell, what you can call it, and therefore, sometimes they are also called as not only coiled fin tube heat exchanger, but fin tube and shell also can be, this can be referred as. The most important or most prominently used heat exchanger is normally which is called as aluminum brazed plate fin heat exchanger. This is very costly item and very difficult to manufacture. However, this is a very compact heat exchanger, that means it has got a heat transfer area more than 700 meter square per unit volume. So, aluminum brazed plate fin heat exchangers are most compact heat exchanger with high heat transfer area to volume. This can either be single or multi-stream. These are widely used in air separation plants and helium plants. And how does it work? What you can see here is you got a fins over here. That could be normal fins, could be U-type fins, could be of different characteristic fins over here. And this fins has a top plate and a bottom plate and a side plate also. So, this makes one layer of the fin. And here you can see that these are made in layers, and there could be 10 layers or 20 layers depending on the flow rate, and all these are basically arranged alternately. So, that high pressure gas goes through, or the hot stream can go through one layer, and if it is a cross flow heat exchanger, above it comes the other gas. So, there are two fluids, one fluid this way, one fluid this way, and therefore, you can understand that this is a cross flow kind of a aluminum brazed plate fin heat exchanger. I got a small unit to show to you here. and this unit can be seen over here. So, this is basically what you can see on, if I show like this, you can see as I have just shown in the figure that you have got a one layer over here and this is a one layer. So, you got a top plate and bottom plate, in which what you have got is a kind of this kind of a model, basically not for this for experiments, and you can see different fins which are kept over here, and the whole thing is aluminum material and it is a braced structure. So, gas can go in this direction, all this will be having one header and the high pressure gas can go through these layers, while alternately you can see that there is the other gas which can go through here. So, hot gas can go through in direction, the other gas, cold gas can go in this direction, which is alternate to this. So, this minimum thickness is basically through which the other gas is going. This is what you can see between these two layers is the other gas which is going from this direction. So, I hope you are understanding that one gas is going this direction below and above of these two layers, and they are alternately stacked. So, one gas goes this way, the other gas can also come down from this if it is a counter flow. In this particular what you can see model, it is a cross flow arrangement. So, one gas is going this way and then alternate layer one gas is going like this. So, all these things can have one gas in a coupled through a header, the gas can go in this direction, one header can be here and other gas is going through direction. Now, there are different fluids that could go in these directions also. So, we can have one fluid going through these top two layers, the other fluid is going to bottom three layers also. Similar thing can happen over here. So, you can have a multiple fluid facilities, heat exchange over here in a plate fin heat exchanger, and one can see how compact it is. And you can imagine such units made in big length of 1 meter or something like that with 10 layers or something like that, then you will have a tremendous heat transfer area that is available in a given unit volume, and this is what we call as a aluminum brazed plate fin heat exchanger. So, coming back, the critical requirement in this is the thermal design and fabrication, because aluminum brazing is not a very simple process, and therefore, because aluminum gets oxidized immediately, and therefore, the aluminum brazing requires a lot of pre-processing and post-processing. So, thermal design is very important depending on the fins, fin efficiency, types of fin, etc. At the same time, the fabrication process also is a very demanding process, and aluminum brazing as it is done in a vacuum environment or a controlled environment, and therefore, this is a very special class of manufacturing or brazing. But this is a very important device because plate fin heat exchangers are very compact heat exchanger. They are definitely are used for all the liquefaction, high flow liquefaction system, they are commonly used. So, the same thing I have just shown here in a photographic manner, so that this is always with you. So, you can see one gas is going over here, the other gas is coming through in this direction. Having seen heat exchangers, let us come to compressors, and in compressors we can see now a compressor is a source of high pressure gas for any liquefaction or a refrigerating system. So, it is clear to us that compressor has to be there so that we get high pressure gas. It is also the biggest source of heat generation due to the motor inefficiency and the gas compressor. Again, this is known to us that the isothermal efficiency of a compressor is a very important thing. Overall compressor efficiency also is a very important parameter. The two broad classes of compressors are reciprocating compressors and a rotary type of compressors. Any of these could be used depending on the flow rates and pressure ratio which we are talking about. The reciprocating types are used for high pressures applications with low flow rates, whereas the rotary types are used for high flow rates and at moderate pressures. So, we can have reciprocating as well as rotary depending on the flow rates and the pressure ratios we are talking about. The losses associated with the compressors are given by isothermal efficiency, adiabatic efficiency or mechanical efficiency or overall efficiency. All these efficiency have to be taken into account in order to calculate the work input to the compressor. Normally, screw compressors and scroll compressors are used for helium gas or nitrogen gas. So, screw and scroll compressors higher isothermal efficiency, low initial cost and more reliability, and they offer a vibration free performance. So, most of the places you will find either screw or scroll compressor, they are actually rotary kind of a compressors and they are being used for most of the cryogenic applications. The compressors being oil lubricated, both these compressors are oil lubricated. The oil content in the compressed gas is reduced by using oil filters. As you know, cryogenics, cryocoolers or cryogenic heat exchangers or liquefiers do not like oil because oil will get frozen, and therefore, all the gas which is coming out of this compressor should be free of oil, and therefore, oil filters are a must. This is a very important requirement that this gas has to be stripped of the oil and only oil free gas should go to the low temperature area. It is further purified in a gas purifier system consisting of activated charcoal bed, so that all the moisture etc. is removed from this gas, and therefore only dry gas without moisture, without oil should go to the heat exchangers and the expanders. Apart from these, centrifugal compressors have better reliability and are used in liquefaction and separation of gases and air separation plant. Depending on the, again, for our very high flow rates, centrifugal compressors could be used. They are also reliable and are used for liquefaction. Screw compressors are oil lubricated and are generally used for high pressure ratios. So, as I said, screw compressors and scroll compressors are generally used for liquefaction of a moderate quantity of gases. So, having seen heat exchangers and compressors, now let us come to the expanders in short, and I will have 3-4 slides on the expanders. So, expanders are used to produce cold. As you know that expanders are very important because it is the one because of which the gas undergoes isentropic expansion and which produces cold in the system. This system must be well insulated to avoid heat inleak from the ambient. In fact, all the heat exchangers, all the expanders should be well insulated here because the heat should not come from the ambient. On the similar lines of a compressor, reciprocating type of expanders are used for low flow rates and high pressure ratio. If you want to expand the gas for a high pressure ratio, then one should go for a reciprocating expander, but then it can take a limited flow rate in this case. On the other hand, a turbo expander is used or a rotary expander is used for high flow rates and low pressure ratios. The design involves high technology and almost zero maintenance. Mostly the new technology is using turbo expanders which run at a very high speed. They are really very good for high flow rates. However, the technology demand is too much, the design is very sophisticated, sometimes have almost zero maintenance requirements. The rough schematic of a turbo expander I am showing over here. So, we have got a shaft which is moving at a very high RPM. One end is a turbine wheel which could be a very smaller wheel, the other one a compressor. On this side, basically this compressor is kept to basically control the speed of this turbine over here. This turbine speed is very high, the RPM could be of the order of 1 lakh or 2 lakhs or around 6,000 to very high RPM in this case. It is an expander turbine wheel and a compressor mounted on the coupling shaft. The work produced in expansion across the turbine wheel is used for the compressor. So, basically compressor is the amount of work which is produced by turbine is not substantial, and therefore, normally this work actually dumped in alternator or sometimes this is and the compressor is basically used to control the speed of this turbine. To ensure high speed, high efficiency for high mass flow rates, turbo expanders in small diameters are operated at very high speeds. So, as I said 3000 to 4000 RPS, which means around 2 lakhs above kind of a RPM which we are talking about, and such a small turbo expander is going to be running at a very high speed, and this is the most important design requirement for as soon as we talk about very high speed, the shaft has to have correct bearings and therefore, very high technology requirements will be there in order to basically take loads of this kind. However, efficiency degrades due to various non-ideal conditions like leakage around turbine wheel, windage loss, finite number of flow passages, etc. So, therefore, as a result of all these losses, you will have some expander efficiency which could be of the order of 75% to 70% like that, or sometimes it could be as high as 80% also, and this has to be taken into account while designing the expander. Turbine bearings, balancing and manufacturing are still matter of research. So, a lot of work is still being carried out in order to design turbine bearings, balancing of turbine on a shaft, manufacturing and things like that. So, a lot of research work is being carried out on the turbo expanders. With this background, having done compressors, heat exchangers, expanders, let us now see the working of liquid helium plant and liquid nitrogen plant. You can see here liquid helium plant, I have got a schematic of the liquid helium plant, and this is the cold box which basically houses expanders, heat exchanger valve, piping, sensors and insulations. So, it has got everything, as I said, different heat exchangers and expanders. So, high pressure gas from compressor gets into the cold box and the liquid is produced in the cold box which goes to the liquid receiver. So, the mist helium, that is the vapor plus liquid come over here, the liquid gets received over here, it is stored over here, and the remaining gas goes back at low pressure and the cycle continues. Now, this is a basically cycle of which we have talked till now, all right. This is a closed cycle, compressor, expander and heat exchangers, the liquid is stored here and the gas goes back and cycle continues. So, from here the users take liquid, use the liquid, or the liquid is transferred from here to even Dewar vessels which are taken by different laboratories for end usage. So, liquid helium is directly used by the users right here in the site, or they could be transferred to different Dewars and different Dewars are taken to different labs. Now, this helium being a very costly gas, wherever it is used, this liquid will get converted to gas. This gas cannot be left to atmosphere, and therefore, this gas is recovered, and therefore there are a lot of recovery lines attached to different utility points. So, all the gas or all the liquid which gets evaporated, which become gas, is stored in a gas bags with these recovery lines. So, here a gas bag is normally a kind of a rubber bag in which the gas is stored, and once it has recovered most of the gas goes to a recovery compressor and it is then pressurized by using a recovery compressor which is different from the main compressor, and this gas is normally called as impure gas because it is collected from various end users, and therefore, they are stored in impure cylinder over here. Now, this impure gas stored in impure cylinder has to be first purified, all right, and the pure cylinder gas also sometimes needs some purification. All right. The purification is a very important phenomena because you have to remove all the possible contaminants like air, moisture, carbon dioxide, etc. from this gas. So, the purifier will purify the gas and then it will go to some intermediate pressure buffer and it will be stored at this point, and from here the gas will be supplied to main compressor and the cycle continues. So, what is important to see here, the liquid helium, whatever liquid helium is used, the helium is not allowed to go outside to the atmosphere. All this liquid, in fact, one says that almost 98% gas which is given in the liquid form should be collected. So, that the recovery is almost 98 to 99%. All right. So, whatever liquid is given to the users, the helium liquid will get evaporated. All this evaporated gas now should be stored. It should be stored in a gas bag. It should be purified using a recovery compressor, stored in the cylinder. The gas should be purified and again the cycle continues. And this is what a liquid helium plant will look like. Now, let us see a liquid helium plant and some specs associated with this. At IIT Bombay, we have got a liquid helium plant, and the specifications of these plants are, this is basically a Linde 1410 machine, model number belonging to Linde company. The output is 15 liter per hour. That means, in 1 hour, it produces 15 liters of liquid helium. The liquefier inlet pressure is 17 bar. 17 bar is basically inlet pressure to the heat exchanger. That means, the gas gets compressed from almost 1 bar to 17 bar, and the expanders in this case are reciprocating time. To understand that they are not basically the rotary type, there is no turbo expander because we are talking only about 15 liter per hour. The moment I talk about having around 100 liter per hour or 200 liter per hour, it will be justified to go for a high flow rate system, that is turbo expanders. Nowadays, even for 15 liter per hour, turbo expanders are being used. The RPM of these expanders is around 230, and sometimes they could be liquid nitrogen cooled also. So, you can have pre-cooling done on this gas. The liquid helium plant has a main compressor which is a screw type compressor. It has got to have a chilled water cooling because the compressor needs cooling, oil lubricated. The suction is 1.33 bar and delivery is 18 bar, and the power input is 80 kilowatt. Now, we can see that 80 kilowatt power input, electrical power input is given to get 15 liter per hour liquid helium from this plant. It demands a lot of power basically. In addition to this main compressor, we have got other compressor which is a recovery compressor. It is a 4-stage reciprocating type, air cooled and oil lubricated. The suction is around ambient and delivery is 17 bar, and this also requires electrical power input of 11 kilowatt. So, once you are operating both the plants, you got both the compressors, you got to have 80 kilowatts over here and 11 kilowatts at the recovery for the recovery compressors. So, the power input is of the order of 90 kilowatt in this case. Then there is a buffer volume of 1 meter cube capacity. The cylinder pressures are around 133.3 bars. Chiller for the main compressor is Blue Star. The temperatures of the water which come out is 11 to 15 degrees centigrade over here. The liquid helium which we are producing used for various end users, one of which is PPMS or physical property measurement system. The consumption is 15 liter per day, while there are other systems like NMR apparatus which requires continuous replenishment of the liquid helium. With this background, I would like to show you a video of the liquid helium plant. Right. So, with this background, with this specification which you just saw of the liquid helium plant, let us have a look at actual liquid helium plant, that is we have with IIT. Now, this is a Linde plant giving you around 15 liters per hour, and what you can see now on the screen is basically all the containers or the devars in which the liquid helium which is produced is kept. So, what you can see here are different containers, and this is around, let us say, 200 liters capacity, around 100 liter capacity, and this is around less than 100, around 80 liter capacity for liquid helium. So, these are different devars, and when you add liquid helium to this, some liquid helium will get evaporated, which is then taken care of in the recovery bags. This is stored in the recovery bag, and this is what you will see now. So, this is a video, and this is around 200 liter, and you can see this is a kind of experimental devar where some experiments could be carried out. From all these things, what you see is there are recovery lines. So, some helium will always get evaporated when you are doing experiments, or when you are filling liquid helium to this, or the helium will always get boiled off. So, on every devar, wherever you see a helium devar, you will see some recovery line, and the helium which is getting boiled off from this is getting stored in a recovery bag which is stored above this, and we will see that later at the end of this video. Okay. So, these are all the recovery lines which are where boiled off liquid helium gas will be stored. It is not let go to the atmosphere as what you see otherwise in nitrogen. And these are the piping, and now let us come to the actual helium liquefier machine. So, this is the helium liquefier machine, and here you can see that in this it houses heat exchangers as well as the expanders. Let us see the video ahead. And this is the most important place where all the action takes place. So, this is our cold box. This cold box houses heat exchangers. The entire liquefier works on Collins cycle. So, you know that there are 5 or 6 heat exchangers, and there are 2 reciprocating expansion engines. Alright. So, this is a cold box which houses all the heat exchangers and the expansion engines, and there will be inside devar, outside devar, and there is a vacuum in between with insulation. And the vacuum is always, whenever you want to start the plant, the vacuum will be made first on, so that the vacuum is always maintained over there. There is a rotary pump, and whenever you want to start the plant, first you will start the rotary vacuum pump, so that you get a good vacuum out there, and then you will start the compressor later. So, this is normally called as cold box, which houses the heat exchangers and the expansion engines, and there are various pressures which are recorded, the vacuum which is recorded, all those dials are shown over there. Many times nowadays these are all digital dials also. Okay. So, just have a close up of the machine, and what you see now here is some display. So, you can see the display where you can always see what are the temperatures at various points in the machine. For example, the inlet temperature, the JT temperature, or the gas temperature before the JT expansion. Also, what you can see is what is the RPM of the expansion engine number 1 and expansion engine number 2, and things like that. So, all the data what is essential for an operator to know, just to know that if the machine is working properly or not, what are the temperatures at various locations, what is the RPM of the expansion engines, all this data can be seen over there, and accordingly the action may be automatically taken, or in some cases if the plant is of older generation, the action has to be taken manually, right. So, this is the display which will be there, and this is now the liquid helium which is produced in the cold box. It will be transferred using this transfer line through the main devar. Now, this main devar is of around 500 liter capacity, alright. So, this is a transfer line which transfers liquid helium from your cold box through this and enters the main devar, and from this devar If suppose somebody want to take liquid helium from our laboratory, it will be transferred from this to the user. This is never touched, this will never go, this always will be associated using this transfer line to the cold box. So, this part is always untouched. From this main DVAR, or sometimes called as mother DVAR, you will transfer the liquid helium to other DVARs. All right. So, let us see the video ahead. And here you will have some liquid level indicator which tells you how much is the liquid helium content over there in the DVAR. Now, what you see here are the moving components, and what you see now here in this direction, you can see now these are the two expansion engines, and the engines are basically kept open in the cold box below, which we just saw. And these are the two reciprocating expansion engine, one on this side, one on the other side. As I said, there are always two expansion engines. There could be 4 expansion engine depending on the flow rates and the flywheel here. Like any IC engine, you got an inlet and outlet valve. So, there are puppet type valves you can see here on either side. There is the inlet valve to the gas, the outlet valve to the gas, and this expansion engine may be moving at 250 RPM, 300 RPM, and as the gas gets cooler and cooler, the gas becomes denser and denser, and in that case the RPM of this will be as low as around 60 RPM. So, that feedback control loop will be there, and depending on the temperatures inside, the RPM of this machine will change. All right. So, you can see these two expansion engines which are moving right now here. So, essentially what you have is a heat exchanger and the expansion engines. So, now let us come to the compressor. That was what the cold box was all about, and this is now the compressor, which is the most important thing. And this compressor now is a screw type compressor, and it compresses the gas from around 1.2 bar to around 17 or 18 bar, all right, with some flow rate of 12 to 18 gram per second of helium. So, you can see this compressor. This compressor is going to be water cooled because the temperature after compression is going to be very high. All right. Now, what is most important is we just saw the other time from the DVAR, from different user DVARs, that the gas goes to the recovery bag, and the recovery bag will get inflated as the gas comes over there, and this inflation is measured in some terms of height of the recovery bag. So, as soon as this inflation of the bag exceeds a particular value, the recovery gas now is will be compressed in a recovery compressor, and it will then be stored in impure cylinder, and this cylinder gas also will be used for liquefaction over a period of time. So, what you see is this is a recovery line, and this is a recovery line connection which indicates gets connected to the recovery bag made out of rubber, and this gas, because it is flexible, because of being in the rubber material, it gets inflated. So, you can see now this is a recovery bag, and as the recovery bag becomes bigger and bigger, then it will be, the gas will be getting transferred to recovery compressor, and this is the recovery compressor now. All right, this is around 11 kilowatt recovery compressor, and what you see now is a user. All right, some property measurement is being done over here in this container here where liquid helium is transferred, and again the recovery line of that will be connected to the recovery bag. So, we can see normally wherever helium production is done, the user also has to normally, preferably sit near the liquid helium DVAR, so that you will not have losses in transferring helium, liquid helium from place A to place B. The users are normally kept nearer to the liquid helium production, and whatever liquid helium boiled off will be there, it will be collected in the recovery bags, and the recovery will be faster and efficient. Whatever helium is delivered, all that helium gas has to be recovered. We should have a recovery ratio of above 98%. That means we should not lose any of the helium that has been delivered in the liquid form. Okay. So, this is an user community who is now nearer to the liquid helium production, and you can see again that the helium gas will go to the recovery connection later. Okay. So, the piping, plumbing has to be taken care of properly to ensure that gas. All right, and they need to have a chiller and cylinders, the infrastructure required. What you saw earlier was water chiller, we supply chilled water for the compressor, and these are the different cylinder, helium cylinder. These are actually manifolds of pure cylinder and impure cylinder. The gas from the recovery compressor is actually stored in the impure cylinders, while there are pure cylinders with which we start the plant. So, we will have a pure cylinder manifold, we will have the impure cylinder manifold, alright, and they both are put to action while operating the helium plant, and this is what in short the video tells you how the helium plant operates. Having seen the liquid helium plant, now let us see liquid nitrogen plant at IIT Bombay. Following are the details. Now, this liquid nitrogen plant is not an open system over here. It uses a Stirling cryocooler with helium as working fluid used to liquefy nitrogen. So, this works on a different principle. It is not an open loop system. This cryocooler generates cooling effect at 77 Kelvin and it has got a condenser. The nitrogen gas comes on this condenser and it gets liquefied. So, this is a closed cycle cryocooler which is running all the time, and the nitrogen gas will come from the top, it will get condensed and what you get is a liquid nitrogen. So, it is a completely different system as compared to what you saw for liquid helium or whatever systems we have studied earlier. So, it basically is a closed cycle while all the other earlier systems were open cycle, that means the working fluid itself used to get liquefied. Here the working fluid just produces cold while other fluid, that nitrogen comes over there, gets liquefied and therefore, you get liquid nitrogen from here. Now, what are the specifications of this unit? The specification of this plant are, the model is Stirling Cryogenics, the output is 50 liter per hour. So, you can see the production rates are higher over here. Now, it has to first produce nitrogen from air. So, air compressor is used and then from air oxygen and nitrogen are separated and nitrogen is then sent to the cryocooler to get liquefied or to get condensed. So, one has to have a air compressors. The power input to air compressor is 25 kilowatt, the pressure is 15 bar. The nitrogen plant has a motor power of 45 kilowatt. If the gas input is of the nitrogen, it will take 45 kilowatt to condense this nitrogen in order to get 50 liter per hour production. The speed is 1480 RPM. The operating temperature could be 67 to 200 Kelvin. What we have in this case will be 77 Kelvin to liquefy nitrogen. Cooling effect is around 4.4 kilowatt at 66 Kelvin. But what we want at 77 Kelvin and the capacity could be around 5 kilowatt in this range. The working fluid inside the cryocooler is helium and it is a very high purity helium of 99.9999 purity. So, very high purity gas is used to run this cryocooler with a mean pressure of 22 bar. So, pressure of helium inside the cryocooler is 22 bar and therefore, the high pressure could be around 30 bar and the low pressure could be around 12 to 15 bar. The chiller is used to cool the cryogenerator and the cooling capacity requirement around 48 kilowatt. The condenser is water cooled and here is what a schematic looks like. This is the air compressor which takes air from atmosphere. The air gets compressed to around 8 bar and stored in an air vessel. This air then is dried so that all the moisture is taken off from here and then it goes to something called as a PSS system or pressure swing adsorption system. And here only nitrogen is allowed to go ahead while oxygen is not allowed to go ahead, assuming that air is a mixture of nitrogen and oxygen. Because of different wall arrangement over here, only nitrogen comes out of this system. The nitrogen gets stored in the buffer vessel at this point and this nitrogen gas then comes to the cryogenerator where continuous 77 Kelvin temperature is produced and the cooling effect of around 5 kilowatt is produced, so that when this nitrogen gas comes from this side, it will get converted to liquid and this liquid is stored in the storage vessel and from this storage vessel, the liquid is given to all the users. So, this is a schematic of the entire liquid nitrogen plant and now I will show the video of the liquid nitrogen plant. So, let us see the video of our liquid nitrogen plant which we have recently bought at IIT Bombay. And what you see here is a 4-cylinder cryogenerator which works on Stirling cycle and this is the common condenser to all the 4-cylinder machine. This is a Stirling cryogenerator and the liquid nitrogen is produced from this side and it is stored in this 2000 liter mother dewar and from here it will be transferred to anybody who wants to take liquid nitrogen from our laboratory. Now, this crankcase, you can see the crankcase houses the crankshaft which compresses the gas and does the compression of the helium gas inside this cryogenerator and this is driven by one motor and the specification of this motor is, as you know, is around 45 kilowatts. The liquid nitrogen generated from this is around 50 liters per hour, while the gas is charged here at 22 bar. All right. So, that means around 10 to 12 liters per hour from each cylinder. Now, what you see from other side is the outlets of the air which are going out, the hot gas, the hot air, because this air which is taken from atmosphere to cool the compressor at this point and to cool the chiller at other point. All right. There is a water chiller requirement because the gas when it gets compressed over here, the temperature increases and there is the chilled water requirement which is supplied by the chiller which is sitting over here, and the air which is getting compressed to basically get nitrogen from is also having an air compressor which also needs to be cooled. So, cooling is done by air only, and the hot air which leaves this place is left outside at some higher point, so that people around will not be getting affected. So, this is the overall structure of the plant. The air gets compressed over here, then air gets in the PSA plant here, which is pressure swing adsorption. The nitrogen is allowed to flow ahead, while oxygen is not allowed to go over here. Here the nitrogen gas comes and nitrogen gas enters the cryogenerator. You will get condensed, and condensed nitrogen or the liquid nitrogen will be stored in this DVAR. This is the in general the plant structure. Now, let us see each component from close distance. Okay. So, these are all the outlet for the air, the hot air which leaves our laboratory. Importantly, you can see that it is a very well ventilated laboratory. All right. This is the air outlet when it cools the compressor. This is the air compressor. Around 25 kilowatt is the electrical power requirement for the compressor, and 45 kilowatt for the cryogenerator here. And then we need, so this is the compressor. So, you can see this is the air compressor which takes air from outside here, and the compressor also uses the outside air to cool this compressor, and the hot air will leave from here, okay, as we just saw earlier. So, once the air gets compressed to around 8 bar, this air will be stored in this air vessel. Okay. You can see it here also in this small schematic over there. So, when the air is getting stored over there, the air then will be dried. That means, whatever water component is there, moisture is there, it will be taken care of. So, we want only dry air to go after that from the air buffer, and from that dry air, this air will go to pressure swing adsorption device, this PSA system. And as you know that PSA will not allow, assuming that air to be mixture of nitrogen and oxygen, the PSA will not allow oxygen to go ahead, and only nitrogen will be allowed to go, and this is done by using molecular sieves. It is like a filter mechanism wherein oxygen cannot go through the sieves, only nitrogen can go through, and once whatever gas leaves this PSA, it will be 100% nitrogen. All right. So, now what is coming out is nitrogen, and this nitrogen is now stored in the buffer vessel. So, here at the end of PSA, nitrogen will be stored and it will be nitrogen pure gas. This nitrogen gas then will go to the cryogenerator for condensation. So, this nitrogen gas will come over here and it will get condensed due to the cold which is produced by this Stirling cryocooler, and it will be stored in this. And then we have got a chiller also to get chilled water from this machine. All right. And again, chilled water plant is cooled by the air, and hot air leaves the laboratory at some higher temperature. So, this is chiller, which is a very important device in this machine, and this is our liquid nitrogen plant functions. And you can see liquid nitrogen being delivered from the main DVAR and put in some 5 liter cryo containers. Okay, having seen both the videos of liquid helium and liquid nitrogen, now I will actually summarize various systems which you have studied right now till now during all the last almost 10 to 11 lectures. The following parameters are kept constant to compare various liquefaction systems studied so far. Working fluid is nitrogen, and initial condition is 1 atmosphere 300 Kelvin. The final condition is around 200 atmosphere for these cycles. 40 atmosphere for Claude, Kapitza and Heland cycle, while 15 atmosphere around Collins and for helium. For Collins cycle using helium as a working fluid. All the equipments are assumed to be perfect. So, if I see this table now here, so first we had an ideal thermodynamic cycle where we get Y as 100% and these are the FOM value and W by MF value. Then I went from ideal to simple Linde-Hampson system and Y got reduced, my work of liquefaction also got increased and the FOM decreased. Then I went to a pre-cooled Linde-Hampson cycle at T3 is equal to 243 Kelvin. What you can see, the Y increased over here, at the same time W by MF decreased as compared to simple Linde-Hampson system, but what I need to do is a pre-cooling. Then I went for Linde dual pressure system where the intermediate pressure was taken at 50 atmosphere and here Y decreases, but what is important is W by MF decreases, that the work per unit mass of gas liquefied decreases, and this was basically the advantage of Linde dual pressure system. All right. If I go for now 1 atmosphere to 40 atmosphere, nitrogen is a working fluid, the Claude cycle I get Y of almost 27%, which is very high. W by MF is 810, while figure of merit also is very high. Then I had a Kapitza system and Heland system where you can again see that Y value is quite high, W by MS is quite low and FOM is also quite good basically in this case, but they are all giving me temperature of around 80 Kelvin. All right, they are all using a single expansion device. If I go for now 1 atmosphere to 15 atmosphere using helium as a working fluid, which is now I am using Collins cycle, and expanders are having inlet temperature of 60 Kelvin and 15 Kelvin with a ratio of 0.4 and 0.2, you get Y at 4.2 Kelvin around 6%. W by MF is of course very high because you got a very small value of Y, and the figure of merit in this case is 0.271. All these calculations I would ask you basically to calculate yourself and compare with this table. The table is shown basically to compare different systems for different end pressure conditions and just to give you a feel of what could be the Y, W by MF and figure of merit for these cycles. In summary, a system which produces cold or maintains such low temperature is called refrigerating system. This process is called as refrigeration. This ratio of delta T by delta P at constant enthalpy is called as JT coefficient. The ratio delta T by delta P at constant entropy is called isentropic expansion coefficient. An ideal gas does exhibit a cooling effect when it undergoes isentropic expansion unlike JT expansion. JT expansion has to worry about the inversion temperature of the gas. Isenthalpic expansion of gases such as hydrogen, helium does not produce cold when expanded from room temperature because their inversion temperature are less than room temperature, whereas gases like oxygen, nitrogen result in cooling when expanded isenthalpically. The isentropic expansion always results in cooling irrespective of T inversion. Now, what we have studied are various liquefaction cycles, and they are ideal thermodynamic cycle, Linde-Hampson cycle, pre-cooled Linde-Hampson cycle, dual pressure Linde system, then Claude system, Kapitza system, Heland system and Collins system. So, we have studied all these systems with their TS diagram with the schematic of those things, and we have solved various problems or we have taken various tutorials to understand how each cycle got evolved, how each cycle become better and better, or how one reaches lower and lower temperatures using various expansion devices, etc. Also, we studied the effect of compressors, heat exchangers and expanders and the effect of those efficiencies on the performance of these systems. So, what is important is to understand how this system function, and one has to be able to do minimum calculations like to compute Y, W by MF, figure of merit for all these systems. Thank you very much.